That's the way to go. Right? I need to use that relation. So I know that before that I use that relation, I have to have some sort of symmetric geometry about the y-axis. Right? Which is right now this geometry is symmetry about the y-axis. And another thing that all my calculations, this distance y is from the line that passes through the center. So I come here, the first thing I say I need to draw that line that passes through the center. So where is the center in this case? It's right here. So you pass a line like that, and pass through the center, right? And that's your neutral axis, right? The neutral axis, in fact, in 3D, is this two-dimensional see that plane that passes through the center. And what's particular about the neutral surface? The stress is zero. The stress is zero at that point. Then you have to change the sign. Negative, positive. So now in this case, I'm happy. Why? Because I don't need to do central calculation. The center is pretty obvious. But I still need to do moment of inertia calculation. Here, I have got a y here, right? So I say, well, the first thing I do, I need to find the moment of inertia of this area with respect to this axis. And that's exactly what I studied in vector statics, if you can remember that. I can break it down. I can do this in many, many different ways. One way, take the entire thing and subtract it by all these four things. Another thing is take area 1, 2, 3, 4, 5. The way I do it here, I prepare is the method that you take this as A. Let's say A1. Take this, A2. And this one, A3. So you break it down into 3 areas. And then you use parallaxis theorem to find the I. Area. One, two, three. Well, you know what, the table is, when we are in vector statics, we do the table just for educational purposes. Here we can just write in one line. I say I with respect to, let's call this x. So this axis, call it xx. So ixx is equal to I come from this guy, area 1. Should I transfer it, yes or no? No, it's already, its local centroid is aligned with the center I want to shear. So there is no need to do parallaxis theorem for this A1. So you just say 112 from here to here. 3 times 50 10 to the negative 3. 112A times B cubed is 50 10 to the negative 3 to the third power. Okay? So that's for A1. What about A2 and A3? I know that both of them are in the same position with respect to the central and they're exactly similar. So I say plus 2 times in parentheses. So in that parenthesis, just one of these guys. So what is this local I? With respect to this axis. 112. from here to here, which is 50 times. The height is also 50. Calculator 3. Now this is a local. 112, 50 times 50 cube is local. Then you have to transfer it. What is your D in that formula? The distance between the local centroid and the global centroid is from here up to here. So what is that? 50. 25 here, 25 here, 50. So you say cross area, which is 50 times 50, everything is 50 here. 50 times 10 to negative 3 times 50 to the 10 to negative 3. That's the area times the distance, which is 50 10 to negative 3 squared. That's your total moment inertia. If you don't know this, I mean, you definitely won't pass this class, all right, guarantee. This semester I want to do structural quality control. If you don't know this, you won't pass this class. So I'll just make it very crystal clear for you. And if you don't know how to compute the moment of inertia, you won't pass this class. What I do in the final exam, I put two questions. One is for moment of inertia calculation, which comes from here, and also shear moment diagram. And I make the weight of this question conditional. That means that I make it like 100% weight. If you can't get it, you get the 0. I don't grade the rest of it. You just get 0, and then you have to take this course again. Well, you have time. You have time to go over this, watch all the videos. I post the video, and then after a week, I see number of views 5. It's like, kindergarten. You say, hey, you're a good boy, Good boy, you study well. Guys, you gotta study yourself. It's not. This is university. It's supposed to be university. Everybody should be serious. I shouldn't tell you what to do. Everything is in a book. A lot of examples, key solved examples on YouTube, tutorial. I mean, when you go home, what are you doing? I see it. When you come here, all I see is just yawning all the time. That means you've been up to like 3 or 4 a.m. That's okay. But you need to study. What I'm saying here is just something I really feel very unsatisfied with the performance. Especially this kind of thing, right now I just got that flat back. Like, come on, this is nothing. And still you see in the exam, out of like 10 students, 2 students only get it. And it's just some sort of like very bad distribution. Yeah. Yeah, that's a parallax theorem. That's this one. You see how I said local I plus 8 times b squared. Now let's put it in calculator. Anyone put it in calculator? So I can just use the value?
I got 8.85 times 10 to the negative 6.
8.85 onto negative 6. I trust you, Greg. Meter to the 4th power. So what else do I need in order to use that formula? The formula says sigma at any point y is equal to negative m over I x x y. So what is the bending moment? Well, in this problem, you don't need to draw the moment diagram. It's given to you. It's right here. In this cross section, the net moment is 40K. So you can just plug it right there. You have moment of inertia. The last thing you need to have is y. And what is y? The distance between that point and the center line. That's your neutral axis. Where is the neutral axis? Right here. Pass through that. So YA is from here to here. YB is from here to here. Right? So all you need to do is just put it over here. So for this, I say sigma at point A is equal to negative M over IXX Y at point A. Plug the value in, you get negative, moment is 40 times 10 to 3 over I, which is 8.85 times 10 to negative 6 times y of A. What is y of A? From here to here, 25. Plus 50, 75. So what should I put here? 75 times 10 to a negative 3. You guys have the soccer match coming in?
Wrestling. And no, we just finished our auction.
You just finished it? When was it?
Friday.
Friday. Did you make any price on it? You got something?
No, we have SoCon in 2 weeks.
Is that the big one that they're talking about it? Look, if you make a title there, I can give you one. Alright, so here, since it again.
I didn't distribute the two correctly in the parentheses, so it was wrong. But it is what I had before, so I'm happy. But it's 1.51 times 10 to the negative 1.51 times 10 to the negative
1.51
times 10 to the negative 5.
negative 5. Like that?
Yep.
Okay. No problem. So here, you see what happened. The computation, you put in the wrong value in the calculator. Now I've got to update. So you have to update that. So you say 1.51 10 to negative 5. So put it in a calculator and see what you get. 40. Negative 198 giga Pascal. Alright? Now, what about sigma B? Sigma point B. It's right here. Sigma B is equal to negative. Moment is the same. 40, 10 to 3. Moment of inertia is the same. 1, 51, 10 to negative 5. And then y is different. Y is 25. Don't forget to 10 to negative 3. That's very easy to forget. I made that mistake too. So don't forget that 10 to negative 3. Yeah. So put in the calculator. That's going to give you negative 60, 66 giga Pascal. Yeah.
Isn't it supposed to be in megapascals? Because it's...
Yeah. Actually, sorry. That's 10 to 6. right?
Yeah.
This MPA. MPA, 10 to 6, thank you. Well, that's MPA. Okay, so now I got the numbers here, and I look at my numbers and it says negative. What does it mean? It's a compression. Then I always want to double check my result. When the moment is like that, what happens to point A and B? You see these 2 points, they compress, and this side is going to extend. You make a little animation, and it makes sense with that negative sign. Alright? Next example. Should we do a meter level? Meter level? Yes or no?
Yes.
One. Here, that would be normal. Whereas at point in the middle, this point is AB. C, at point B. At point E and B prime. Put the prime here on top. B prime. So B is at the very center. You see that? In the middle, at the very center. B prime is again in the middle, but is on top of the beam. Now there is a hint here. Use superposition. Use principle of superposition. We already talked about it in the last class. Use principle of superposition to find the stress at point B and B prime. Now, if you get the value for B prime, that is going to be considered as a meter labor. Now, the way we do it, instead of me asking you to write it down, because we don't really have time to give another 4 minutes for that, I ask you, you have only 60 seconds to make a decision. To come to the whiteboard and show it, or draw it. If you can do that, then you get a waiver. Otherwise, I'll just charge myself. And we only have one student. The first to come, get the waiver. You see, he already has 2 waivers, and now he gets 3. You want to do?
Oh.
No? You can get 6 meter waivers. Now we have 2 meters. What happens to the rest of 3? Well, it's going to be added to the final exam, to the homework, to the quizzes, to the everything. Right? We have quizzes. It's not only a meter. We have finals, we have quizzes, we have homework. You see, the end result will be a function of M, F, L, and the diameter. The end result is a parametric solution, yes. The end result is a parametric solution. You don't need to use calculator. So what was the principle of superposition? The principle of superposition says what was that 16? Yeah, that is correct. Well, almost. Hold on. I want to reach that. I like a solution posted by Kim, but that's not still very correct. But the way he taught is your approach is correct. This superposition, this comes from the axial load, this comes from the bending moment. But when you put, that is not correct. That is not correct. Yeah, when you put R0, what do you get? You see, at point, that's what, this one, that's what, that's right. Actually, I accept that. That's completely right. Thank you. That's right. He does good mathematics, Kim, and he got, I had a solution, I had a very complicated problem in the last mechanical material, and he could solve it, and I was very impressed. So that's good, that's really good, thank you. So here, what he did, he said, principle of superposition. Principle of superposition says, if you have many loads, just consider one at a time, and then add the result together. So that makes your job easier. So instead of considering two, I'll just consider first, let's consider the axial load. There you go. So that problem is this problem plus when you only have the bending one. Fm. This plus this. So I solve each one independently and add the result together. So for this one, what would be the stress, the normal stress at point B and B prime? Most of them is sigma B prime is equal to negative, don't forget the sign, negative force divided by that cross section. You see, this cross section, if I call it like that, then you're going to have a circle. And assuming that this is far away from this point, you see here you have a stress field is like this. But here the stress field is uniform. You see that? Sigma is same. So you say sigma at B prime is equal to sigma at B negative force divided by the cross-sectional area, which is pi r squared. Now, what is my r? D over 2 here. Then you can get that number. Right? That's what you got. For most of them. You see? Here. Now, what about this point? When we have only bending moment here. When we have a bending moment, then we have, if I call it like that, then I'm going to have something like this. Right. Compression, tension. So top is compression, bottom is tension. And the center is 0. So here I can write sigma B prime. Are they equal in this case? Yes or no? No. So sigma B prime is equal to, where is B prime? Right here. So I use this equilibrium. So I get negative. Bending moment there is what? N divided by I, which is pi over 4, the radius to the force power, times y. And y is equal to r. With the negative sign. What about sigma B? sigma at B. Again, I have negative m divided by moments of inertia times y. What is my y at B? 0, right? 0. So it's 0. So add them up together. You see there is a plus sign here. So the end result for sigma b is sigma b coming from here plus sigma b coming from here. So it's negative f over pi r squared. What did you get? Negative f over pi r squared. And then sigma b prime is sum of these two. Here you have negative f over pi r squared, and here you have negative m over pi xx, which is basically what he's trying to say is this one, right? Times r. You see that? Now, I want to give you something that this is, we talked about two particular points, dv prime, right? Now, I want to talk about something called field, the stress field. When we say field, we are talking about infinite points here. So in fact, if this is my beam, right? A point here, a point here, a point anywhere, anywhere. So your sigma is a function of the field. You remember in the geometry, analytical geometry, we had three-dimensional Cartesian cylindrical coordinate system, Cartesian coordinate system, spherical coordinate system in order to explain infinite data, the field. Now the question is, assuming that there is a point, let's say the point x here, take it from the left, x, and located with location y from the centroid, y. So express your sigma as a function of x and y. That means field. Find the stress field, not the stress at point. Find the stress field. So how do you find that? So your x is from the left side of the beam and y is from the centroid. The end result, sigma should be a function of x, f of x and y. How do you find it? Exactly the way you did, using superposition principle. So you first consider F only, and then you consider bending moment only, right? If I consider only F, everywhere it doesn't depend on X, right? Anywhere you're going to get this one. Now, if you consider the bending moment, then your stress is going to be this one, but it depends on y instead of r, right? When you sum them all together, you find out sigma of xy becomes negative f over pi r squared plus negative m over pi over 4 r4 times y. In fact, that's only a function of y. Right? That's only a function of y. So what is my maximum? You remember in the calculus, the basic calculus, you had a function of several variables. X, y, z, yeah.
The maximum radius is the maximum stress.
The maximum?
There's maximum.
It would be the max end.
Y.
Yeah, the maximum of this function, whatever it is. How do you get the maximum function? You take the gradient, make it 0. You find the max externally. That's exactly the same. So I'm converting a mechanical problem into a calculus problem that you know alpha angle. How do you find the maximum function? Take the derivative, make it equal to 0. Right? So this is a general function for any point. So if I say evaluate at this point, let's say this corner right here, what do you put there? x0 But you see that function is in the limit of x. Well, you say that at this point, x0, y is what? Negative 1. You put it there, and you get a stress for that. What about this point? x0, y is equal to positive 1. You put it there, you get a stress for that. Okay? You have a question? All right, next example. Now let's do this. Let's solve this problem. F1. F2. And the bending moment. And now express, assuming that this cross section of this is like symmetric, and have IXX. Express sigma as a function of x and y. For any point, so this is like a stress field. It's valid for points, field. So let's say x is the point from there. This is your x. And y is the point from the centroid. This is y plus, 1 minus is under it. Look, x could be from here to here, and from here to here. So we have two intervals. You see that? Because we have a force here with it. Let's give some values to these numbers. So let's say F1 is equal to 1K, F2 2K, and moment is equal to 3 kilonewton meter. Now for this problem, find the stress field. That means find sigma in terms of x and y. Solution. What should I do? The first thing I do? Superposition. Right? So if I do superposition, how many problems should I solve independently? Three problems, right? So let me draw the three independent problems here. So one problem is when you only have 1K here, plus when you have 2K this way, plus let's say 2K, and then the last one is equal to, when you have a bending moment, 3K this way. Algebraic sum of this with considering the correct sign, positive or negative. You got to consider the correct sign. It's the result to the problem according to the superposition. So for 1K, what is my stress field? First of all, how many intervals should I consider? 2. From 0 to L over 2. So let's say your L is, this is 1 meter, and this is 1 meter. So it's from 0 to 1, from 1 to 2. So if I consider from here to here first, what would be my stress field? Sum of this, which is 0, Is it 0? No, because it's 1K, we still have it here, right? So sum of this is what? The stress here is what? Let's call it 1, 2, problem 3. So sigma 1 is equal to 1K over the cross-section area. Positive or negative? Negative, it's compression. What about this one? Here you have 2K, right? If you do external reactions here, then there is a 2K this way, 2K this way, so it's positive. So you have sigma 2 is equal to positive 2K over A. And what is A? I over 4 P squared. If you have gone into here. What about this guy? Is equal to sigma 3 negative M, which is 3K, times I, Y. Now that's not the number. That depends on how much you have deviated from the center. So this is center of the point, right? This is your Y plus, Y minus. So from here to here, if you just sum them up together, your total stress is equal to sigma 1 plus sigma 2 plus sigma 3, which is 1K over the area minus 3K Y over I. From here to here. So there is a 2 minus 1. So positive 1K over A. So now from here to here. Now this was from 0 to 1. From 1 to 2, what do I have here? Sigma 1 is still negative 1K over A. Sigma 2 is equal to? Let me ask you. Sigma 2 is equal to?
2K over
But that's a mistake everybody makes. That's a mistake everybody makes. Let's think it one more time. Right. So you see the support is here. So if I just consider 2K, you see superposition, I'm not considering that. You see I have 2K here, right? So there is a 2K here, but here is 0. That's the mistake that almost 99.1% of the students make. It's extremely easy to make a mistake here. So that's what I'm saying. If you have extra time, I usually give extra time. Do not turn in your paper. Just go over everything you have done, but criticize yourself. Don't trust your eyes. Just go over all the basic formula, make sure that you have all the sign. So here, sigma 3 is equal to 0. What about this point here? Sigma 3 is equal to? Again?
Negative 3K. See that, the same thing, right?
0. Look, only consider 3K. And you support this here. You see? Then call it from here to here. You remember we had moment. Draw a moment diagram. What do you get if you draw the moment diagram? You get positive 3K here from here to here, and then you have 0. That means if you cut this from the right, nothing is supporting it. It's supported from left to the wall. So the bending moment is also sigma 3 is 0. So sum them up together, what do you get? Sigma is equal to negative 1K over A. So if I want to write this using a mathematical relation, I say sigma x and y is equal to the first relation, which is 1K for area, I put pi b squared over 4 minus 3K y over I, which is pi over 4 R, the force power, so that's 16 4 times 16 D4. That's when x is equal to the smaller than 1 greater than 0. Now you get negative 1k over y d squared over 4 when x greater than 1 less than 2. Now look, your stress field depends on both x and y right now. You see that? X dependency is right here, and y dependency is here. So you have a function of two variables. When we had vector calculus, when we had the calculus 2, they were talking about a function of 6 variables. And we said, what's the meaning of that in the actual life, in the real life? That's the meaning of it. You can have a stress field function of 10 variables. Okay, 10 different things. But let's say you design, in fact, that's the way the CAD software do it. Let's say you have something like that. And you know, this has different parts. Part 1, part 2. You see, you design something in CAD. Each one of these has a thickness, length. Each one of them is a variable like this, x and y. You measure thickness, right? And then you modify something here. You go to the CAD software and say this L was 2, now make it 1, enter. And then everything is going to be updated automatically. What it does, it just does calculus 2, function of many variables. That's exactly what it does. We have the same thing for stress over the entire here. So if I want to find the stress here, what should I put in this formula? If I want to find the stress right here, what should I put for x and y in that formula? X is equal to 0, y is equal to the radius, or r, d over 2. So which one? I go here, x is 0. Should I use that or this? The top. And y is equal to d over 2. Put it here, put it in the calculator, get the stress. It gives the stress over the entire dome. Alright, so one more example. We have something called 4-point test. We have mechanical material lab with me, or you are currently having that. When you have a scheme like complicated cross section like that, this is beam, and then we fix it in a machine. This is from left, and we apply loading here. These are the support. So let's put a roller here, another roller here, P over 2, P over 2. So when you apply loading to that, this is going to be formed like this. Right? It's going to go down. Then you have deformation. Now the question is, find the maximum stress. Assuming that you know the centroid. So let's say here is the centroid. From here to here is C1. From here to here is C2. C1 and C2 are measured and given to you. So let's say they're just numbers, C1 and C2. And IXX is also given, it's just a number. This x is x. IXX is given, C1 given, C2 is given. Right? In fact, you can find this by putting the number in the online calculator, or you're doing it by hand. We do both methods in class. So then you get this problem, and now the question is find the maximum stress. Find sigma max. I'm talking about the absolute value. And show the location. Show its location. So that's the question. This can come in the exam. I can give you these values and say, give me the numerical value of maximum stress. Is that going to happen in top or bottom? Where? In the middle, at the corner. So what do? How do you know that where the maximum moment happens? What do you do in order to find the variation of moment? The moment diagram. The moment diagram. So if I want to do it correctly, I would draw a moment diagram. Right? So in order to draw the moment before I actually use this equation. And let's say I find the maximum moment from the moment diagram. Then what do? I use this relation. But which one am I going to use for y? What quantity should I use for y? C1. You see, C1 has a greater distance than C2. So the maximum moment happens right here. So it has more deviation from the center. So this is going to be my C1. This is the moment of inertia. So you have moment of inertia, you have C1. And all you need to do, in fact, this problem is the problem of drawing the moment diagram, because all you need is the actual maximum moment. The rest, I'm just asking what the absolute value of that moment. So you do mark by maximum moment by C1 divided by I. And C1 and I are also used. You don't need to calculate it. So this takes probably 2 minutes to do that. So if I want to find moment diagram, so this is making it small in meter waiver. If you can draw the moment diagram for this. And this is P over 2. I will give you the number. Draw the moment diagram. On the whiteboard, and only one student. You cannot do it simultaneously.
Well, I mean, it's like chicken. Short extend.
You don't want to write like the values over there, like positive, negative, and what, PL, P over L2.
Yeah.
There should be some like.
Some calculation for it. I just remember that.
You just remember, no, that's not the way it works. Thank you for coming. In fact, that's good that you want to contribute. But what I'm saying is, find it. You know, I know that in the lab manual tutorial, there was a moment diagram that was drawn there, so you just see, okay, this goes like that. But how do you find that using the method we taught in this class? Let's go over the procedure. What was the procedure? Take a reference point either from left or right. And then start writing it. How many intervals do I have? From here to here, 1. From here to here, 2. From here to here, 3. In each interval, find the internal moment. So from here to here, what do you get? First of all, the external reaction. What do I have here? P over 2, P over 2. If you don't believe it, just put AY, BY, and write sum of force AY plus BY is equal to P, and write it. Moment over distribution, you realize AY is P over 2, BY is P over 2. Now, cut it. Take X from left, cut it. X between 0 and this point. Say A. From here to here is A. Whatever. Call it C, D, whatever you want. So if I call it there, what do I get for FBD? P over 2. And then you have a bending moment this way, mx. I don't care about shear. Why? Because if I get the bending moment, I take the derivative of bending moment and I find the shear diagram. So, summation of moment, what point x, 0. What do I get? Mx plus this plus mx. See, positive mx. Right? Plus the moment come from this guy. What's the moment come from that? Force times moment arm. P over 2 times moment arm is from here to here, and from here to here is x. So P over 2 times x, positive or negative? You take your right hand, negative. Is equal to 0. Solve for mx, your mx is equal to P over 2x. Then I want to draw it here. So from here to here, from here to here, and from here to here. 1, 2, 3, 8. So if I want to draw it here, what do I have? I have a line. What's the slope? A positive number. So the line is like this. Because the slope is positive. How many points do I need to draw it?
2.
At 0 is what?
0.
At point A is what?
P over 2.
PA over 2. So you have a line like that. Now let's go from here to here. Between A and this point is L minus A. Right? L minus A. So A to A, L minus A. I'll do a FED. FED will look like that. P over 2. And here, P over 2. This distance is A. And from here to here is X. Right? So P over 2, P over 2 this way, A, and then this distance is X. So M of X, summation over here, M of X, plus P over 2 times X minus A, negative P over 2 times X is equal to 0. If I wrote it correctly. So here, between you have a bending moment, so I put it here, M of X, P over 2 at A, and P over 2 here is bottom. And from here to here is X. So M of X plus P over 2 times this distance, which is X minus A. Right? Then negative P over 2 times from here to here. X is equal to 0. So expand that. Then you get M of X negative P over 2 times A. This P over 2x cancel out with negative P over 2x is equal to 0. So what is your bending moment in that integral? PA over 2. How many points do I need to draw that? Just 1 point. You see? You already have PA over 2. You just continue that line. I'm getting his character. But I'm getting it from the method we studied in this class. I didn't memorize anything. And then what do I get from here to here? Well, you can do the same thing, or you can just say, well, it's perfectly symmetric. So if I just flip it the other side, what do I get? That's my moment diagonal. So what moment should I use? This one. When I put in this equation, I use PA over 2, this is C1, and this is IXX. All these numbers are given to you. So you multiply 2 floating numbers divided by 2 other floating numbers. 1 minute. And then you get a final result. That's it.